In this lecture, we are going to start Chapter 10 in Griffith's book on electrodynamics. And Chapter 10 is on the concept of potentials and fields. So our goal up to this point has always been to try and solve for equations for electric and magnetic fields. Now we're into a part of the course where the electric and magnetic fields are time and spatially changing, which means they produce electromagnetic waves, oscillating electromagnetic waves. So before this chapter, basically in Chapter 9, what we dealt with is the case of no sources. So when we mean no sources, what we're talking about is there is no free charge and there is no free currents. So that simplified things because now we can have an electromagnetic wave which is oscillating through space, and it cleaned up the solutions to Maxwell's equations quite a bit. It made the electric and magnetic phenomenon basically similar to each other. So now what we want to do is we want to generalize a little bit more and put in free charges and free currents. In order to solve this problem, then it's going to be easier, what we'll find to be much easier to solve it in terms of potentials, electric potentials and magnetic potentials. So like all problems in electrodynamics, we like to start with Maxwell's equations. So I can write down Maxwell's equations. Okay, so these are the four Maxwell's equations. And so like I said, these are a little bit tricky to solve. It's now going to be kind of difficult to solve things like the curl of the electric field for a time-dependent magnetic field. So what we want to do is try and change these vector derivatives, the curl and the dot products, into things like a second-order differential equation where we give up some of that complication. So let's start with stating that the magnetic field is the curl of some vector potential. And this is always true because the divergence of the magnetic field is zero, basically from Maxwell's second equation. But if we do that, we can now put this into Maxwell's third equation and write down that the curl of E is equal to minus the time derivative of the curl of A. And now we can choose which one of these derivatives we want to apply first, whether we want to apply the curl of A first or the time derivative of A first. So if we switch it around, what we would have is minus the curl of the time derivative of the vector potential. Now if I add that to both sides, I would get the curl of E plus the curl of my time derivative of the vector potential, and I'd set that equal to 0. Now I can essentially factor out all the vector parts, and I'm left with the curl of an electric field plus the time derivative of a vector potential, and I can set that equal to 0. Now if you remember from the beginning of the course that the curl of a vector function that's equal to 0, I can write that vector function now as minus the gradient of a scalar function. So I can write this now as the electric field plus the derivative with respect to time of a vector potential is equal to minus the gradient of a scalar function, which we call the electric potential. In doing that, I can now rewrite the electric field as minus the gradient of V minus the time derivative of A with respect to time. And now I have a very general solution for the electric field. Electric field, when we're talking about statics, no time, all the time derivatives were zero. The electric field was just the gradient of the electric potential. But now that we're allowing a time change or time derivatives into the problem, now the electric field is a mixture of a electric potential and a magnetic potential. So this is, like I said, is a more general result. So now if I take this, plug it back into Maxwell's first equation, which is Gauss's law, so I then have the divergence of the electric field is equal to the charge density divided by the permittivity, epsilon naught. Okay, so then when I apply that, I get minus the second derivative, or the Laplacian, of the electric potential minus the time derivative of the divergence of the vector potential. And that's equal to charge density over epsilon naught. So just to kind of clean it up and make it look a little cleaner, make it a little better, then I'll multiply both sides by -1, and I'll get now this thing, which is essentially a second order differential equation. Okay, so now this is the approach that we're going to take, where now we've rewritten Maxwell's equations with a charge distribution in it into a second order differential equation. It still looks a little bit complicated because we've got a divergence of a vector potential and then time derivative of that. But don't worry, we're going to clean it up a little bit more. If this is 0, which is essentially the magnetostatic case, then we return to our statics solution, which we saw when we just looked at static electric charge. Okay, so that's good. Okay, so now let's try if we can do some more to this. So let's now substitute into Maxwell's fourth equation, the Ampere-Maxwell equation. So the curl now of the magnetic field becomes the curl of A, our vector potential, which is equal to mu0 times our free current. And now we have to substitute in for the electric field. So that would give us minus mu0 epsilon naught, the gradient of the time derivative of the vector potential, of the scalar potential, minus mu0 epsilon naught, and now we have a second derivative of the vector potential with respect to time. So all I did was take Maxwell's fourth equation, plug in what we now know for the electric field in terms of potentials, as well as the magnetic field in terms of the A potential. Okay, so now this looks a little scary too, but hold on tight, we're going to do fine. Because we can do a vector substitution, which says the curl of a vector is del of the divergence of that vector function minus the Laplacian of that vector function. Okay. Okay, so if we plug that in to what we have up here, then we would have del now we get that equation. And if we now try to bring all of the a's to the left-hand side, then what we would have is minus Laplacian of a plus mu 0 epsilon naught second derivative of a with respect to time plus the gradient of the divergence of a plus mu 0 epsilon 0 the gradient of the time derivative of v, and all of that is now equal to mu 0 times the free current. Okay, so if I can now combine my some terms together, what I get is Laplacian of a minus mu 0 epsilon 0 second derivative of a with respect to time. So I'm going to group that together, minus the divergence of, the gradient of the divergence of a plus mu 0 epsilon 0 time derivative of v. And all of this is now equal to minus mu 0 j. So what did I do? I multiplied a minus sign on both sides. I grouped together the terms, so now all the gradient terms are in that square bracket, and left the other two. And so now what we have is all of Maxwell's equations written into a single equation, which it doesn't have any more fields in it. All that it has is potential functions. It has the vector potential functions, like A. So it has this stuff, which looks like a much cleaner second order differential equation. And we now have this stuff right here, which is the anything that has to do with that gradient operator. And all of that is now equal to the source, which is the current, the free current in the problem. Okay, so before I go on, let me go back and now just try and write this in a much cleaner fashion. And that is to write down this, what I call the second order differential equation piece to it. Minus the gradient piece to it. And all of that is now equal to minus mu 0, the free current. Okay, so that's it. So now what we can do is, we've got basically a second order differential part, another kind of first order derivative part, which then you have to take the gradient of, and then you're home free. So in the next lecture, what I'll do is we'll kind of go over an example of how we can apply these equations.